See, no.
Yes.
Okay, thank you. Okay, so may I confirm, Ying Sun, are you here? Ying? No? Okay, so then we may kind of reorder the sequence, okay? So, so let me give a very quick introduction to this section. Okay, so welcome everyone. So this is Yong-Hong from the University of Hong Kong. So in this section, our title is Urban Mobility in China. So we are honored to have a few great speakers who will share their research in different types of for different types of transportation modes, including vehicles, bikes, sharing systems, also railway system, and also behaviors for pedestrians. And so this section is jointly organized by our BTR and also the Institute of Transport Studies. And each speaker is given around 30 minutes, including the presentation. Okay, so the presentation, and also maybe like 20 to 25 minutes for the presentation, and then around 5 to 10 minutes for the Q&A. And then, as I mentioned, the first speaker, we had some difficulty. Okay, so probably maybe it's about the information about the schedule. I think currently I don't see Ying on site or online. So now you see actually we have this room. Okay, so this physical room to host this section in Hong Kong. So without further ado, I would like to invite the first speaker, Dr. Jia Cui, to share her research. The title is Optimizing Battery Swapping and Bike Repositioning Strategies for Electric Bike Sharing Systems. Okay, thank you, Dr. Cui.
Testing. Thank you, Professor Guo. And I'm Jia Cui, and this talk I will introduce electric bike repositioning problems involving the battery swapping and bike relocation. And this work is cooperated with Professor Sito and Dr. Wang Yue. Oh, oops. Sorry, I cannot. Oh, okay, sorry. Let me first introduce some background and the motivations of this study. The shared micromobilities, including the shared bikes, e-bikes, and e-scooters, has been an important means of transportation in the first and last mile problems, and it helps to connect other transit modes. And the scale of the micromobility have expanding in recent years, especially during and after the pandemic. Sorry, okay. Among these shared micromobilities, the bike sharing systems has been one of the most indispensable and one of the earliest components. It is designed for the short-term urban communities, and it is, of course, affordable and accessible to most citizens. And people can rent, return, or relocate the shared bikes through the mobile app, and they can pay for their trips. Apart from the conventional bikes, the e-bikes have also been an popular means of transportation, and the e-bike sharing systems have gained widespread popularities. Different from the conventional bikes, the e-bikes are motored with batteries, and it supports longer distance with lower physical consumptions. And many popular and large bike-sharing operators like Lyft, Lime, and Qingju Bikes in China have successfully deployed the e-bike sharing systems. Despite the benefits or the development of the bike sharing systems, we can still observe some challenges. First of all, the bike sharing systems suffers with the imbalance between the supply and demand, because people normally travels from the residential areas to the commercial areas in the morning and return in the afternoon. So some areas may suffer from excessive of bikes, while others are in shortage. And this imbalance will bring some user unsatisfactions. And to tackle these problems, the operator needs to relocate the bike from the areas in surplus to the areas in shortage. And this problem is what we know as the bike rebalancing problems. Sorry, the network is really slow. Okay, this is what we know as the bike rebalancing problems, and it has been widely studied and have many branches. It can mainly divide it into the vehicle-based and user-based. Also, it can divide it into the static and dynamic due to the timing of the rebalancing. And we all know that the bike rebalancing problems is a variant of VRP problems. And the bike rebalancing problems we study today are at least NP hard. Okay, the second challenge is specific to the e-bikes, because the e-bikes are motored by the batteries, so it easily become unavailable when the battery level is low. And the low battery e-bikes may hinder the pavement and cause some safety problems. So the operators need to properly collect or recharge these bikes. Nowadays, there are two popular means of recharging. One is using the charging pile, another is using the battery swapping. Compared with the plug-in charging method, the battery swapping can restore the battery level very quickly. Although the advantage of the charging method, charging itself cannot fully satisfy the demand of the e-bikes, so the e-bike charging should incorporate it into the bike rebalancing process. Through the literature review, we find that existing literature on e-bike sharing or e-bike repositioning problems have focused on the charging in addition to the rebalancing. But we still find that the existing studies still separate these two tests into the different fleets. And existing studies also did not consider the large-scale network optimization. To fill these gaps, we proposed a new multi-vehicle static e-bike rebalancing problems with considering simultaneous battery swapping and e-bike relocation. And we formulate these problems as an MILP model, and we propose a hybrid genetic search with two new heuristic loading strategies to solve the large-scale networks of these problems. So next, I will formally introduce these problems. In this e-bike sharing systems, we have a set of e-bike stations and one depot. And we have two status of the e-bike. One is the functional, another is the low battery. The low battery e-bikes availability can be recovered by the battery swapping. And we deployed a homogeneous fleet of vehicles to do the rebalancing. Each vehicle departs from the depot and travel among the station and finally return to the depot within the time budget. And we need to determine the routing of the vehicles and also the loading, unloading, and battery swappings at each station. And our objective is to minimize the total rebalancing cost. And to formulate this model, we define the following decision variables. And to minimize our objective, we consider several components. The first component is related to the penalty cost, related to account for the bike and dock deviations. And the second component is the fixed cost, account for the usage of the vehicles. And the third term is the travel time cost. It is very common in BRP or VRP studies. And last, we incorporate a weighted term of total loading, unloading, and battery swapping quantities to reduce some redundant solutions. Also, we determine the constraints related to the routing of the trucks, loading, unloading, and battery swapping limits, and the station and truck capacity, as well as the time budget limitation. Also, we incorporate software eliminations. As I mentioned, this problem is NP hard, so solving it directly through the solver can be computational expensive. Alternatively, we proposed a hybrid genetic search with two loading strategies. The hybrid genetic search is based on the hybrid genetic search with adaptive diversity control proposed by Vidal et al. In 2012. And we choose this method mainly because it effectively solved the multi-type bike rebalancing problems by Li et al. In 2016, because we also have two status of the e-bikes. And the hybrid genetic search is different from the traditional genetic search because it incorporates the diverse control, local search, and the diversification of the populations. And the hybrid genetic search structure is mainly designed for the road searching. And for the specific instructions for the loading, unloading, and battery swapping at each station, we proposed two novel and problem-oriented loading strategies based on different ideas. The first strategy is a more globalized strategy heuristic. It first determines and estimates the total number of the batteries required for the whole roads. And then we calculate the number of functional e-bikes required to relocate throughout the roads. And finally, we utilize the remaining truck capacity to collect the redundant low battery e-bikes. And in comparison, the second strategy, we simultaneously determine the number of battery swap and the functional e-bike relocation at each station. And finally, we also collect the redundant low battery e-bikes. And either loading strategy will go through an improvement algorithm to reduce the penalty cost related to the bike and dock. And after determining the routing and the specific loading and unloading instructions, we will evaluate each solution by a function consists of the original objective function and a penalty term account for the infeasibility. The last part, we test the effectiveness of the proposed algorithm as well as the correctness of the model. These are the parameters we used in the numerical experiment, and most of them are inherited from the related bike rebalancing studies. And the network of our instance are selected from the dataset used by Ho and Seitu in 2017, based on the city bike data in New York. First, we conduct a sensitivity analysis based on some key parameters. First, we test the different percentage of low battery e-bikes in the system. And we find that when the low battery e-bikes is relatively low, the battery swapping can help to supplement the functional e-bikes by transfer the low battery e-bikes into by recovering their availability. But when the low battery e-bikes becomes excessive in the systems, the limited resource of rebalancing will not efficiently handle these redundant bikes and result in the increase in the dog deviation and handling cost. Then we test different ratio of loading, unloading, and the battery swapping unit time, and we find that our system is, although we cooperated the battery swapping for recover the low battery e-bikes, the system is still sensitive to the change of the unit time of loading, unloading, and we can conclude that the bike rebalancing or bike relocation is still necessary in addition to the charging methods. And we also compared our proposed rebalancing strategy with the benchmark strategies from the literature. And we found that the proposed strategy is efficient compared with the fixed truck capacity and separate fleet operations by Xu et al. And Zhou et al. Then the first part of our numerical experiment is essential to test the effectiveness of the proposed hybrid genetic search. And the most parameters used in the hybrid genetic search is referred to the Li et al. And Waddell et al., but go through a parameter tuning to fit our studied problems. First of all, we compared the hybrid genetic search with Groovy in the relative small networks. We allow the Groovy to run optimality or out of storage to obtain the optimal solution or the optimal upper bound. And we also compare the hybrid genetic search with the upper bound we obtained. By the comparison, we can easily see that the hybrid genetic search can obtain the optimal solution in less CPU time. Then we extend the comparison in the larger networks, and we limited the Groovy and hybrid genetic search to terminate in 2 hours. And we compare the best solution obtained by hybrid genetic search with the upper bound obtained by Groovy. And the result is obvious that the hybrid genetic search can outperform the Groovy in all instances. Then we also compared did this comparison in large networks with different percentage of the low battery e-bikes, and the hybrid genetic search outperforms Groby across all the instances. As we have two different loading strategies, we also did a t-test on the results of the larger networks to see whether the two loading strategies are, which strategies performs better. But from the t-test result, we found that the two loading strategies are equally good statistically. We also include a comparison between the hybrid genetic search framework with tableau search, which is also a meta-heuristic, but the hybrid genetic search is population-based and the tableau search is search-based. And from the result, we found that the hybrid genetic search is more efficient to solve these problems. And the reason behind is that the hybrid genetic search will increase the diversification, and the local search will effectively improve the solution quality. So in this talk, we proposed novel e-bike rebalancing problems with optimization with both battery swapping and e-bike relocation. And we did a series of sensitivity analysis and explore some features and some managemental insights of these problems. And finally, we evaluate our proposed hybrid genetic search in larger networks and confirm its effectiveness. And this is all for today's talk.
Okay. Thank you. Thank you. Okay, Dr. Che, for the for a comprehensive presentation. We do have some time for questions. Questions, or like for those online, you can unmute yourself, or you can type your questions. Or I can start with my first question. So in your optimization framework, like do you think like in practice, like how large the scale is, like how many bikes, or like how many stations, or like so what would be like the realistic problem instance or scales? And my next question is, typically when we consider bike repositioning, right? And then we'll consider real time, something like, or dynamic decisions, like whether in your framework you could take care of these kinds of complexities, or like whether you could extend your framework for these more like larger scale, or like more realistic instances.
Thank you, Professor Guo. And the first question, we tested the city bikes up to almost 500 bike stations, and the running time is relatively fast. And we believe that this algorithm can tackle larger scales in reality. For the second questions, although this problems is a static setting, and the future studies or some working papers have already considered the dynamic bike rebalancing, and we can actually use the time rolling horizon methods to divide the whole process into different horizons and solve with these problems. We can regard each horizon as a static bike rebalancing problems. Thank you.
Good. Do we have further questions from any of us? Yep.
Thank you for your presentation. So I just have a quick follow-up questions. So do you think in your framework, maybe in the future work, let's say, is it possible to take the travel time or the congestion level into the situation? As you mentioned that in some studies, they consider about the dynamic process. So probably, I'm not sure, is it possible like in your framework, you can incorporate the travel time, like while you do the battery swapping across different regions or different stations?
You mean using the real-time traversy?
Yes. Just like let's say in the future.
We actually use the local bike data in Hong Kong to tackle free-floating bike systems in my current study.
Okay. But
This
it's not the real time, like the
it's
real.
not the real time. We will conduct step by step.
Okay, that's good. Yeah, thank you.
Do we have further questions? So I have another question, another aspect, not on the computational point of view, but thinking about this e-bike application. Actually, to my understanding is if we use a bike, okay, so traditional bikes, typically we consider is environmentally friendly mode, right? Transportation mode. And then I'm thinking about like if we have electric bike, then you also need to generate the energy, right? Yeah, so then I'm thinking about like how do you see if we use electric bikes for transportation, maybe we can say, okay, so within the city we have less pollutants, I mean, environmental footprints, and also it may be healthier, right? So you do the sports. But in terms of the environmental impact, in terms of the energy generation, whether like in the literature or other studies or like in the industry, so they have considered the impact maybe not in the urban environment, but maybe they just shift it to elsewhere. How do you see? Maybe it's still like environmentally friendly, maybe less, carbon footprints or whatever. Do you have some for us or like some ideas to share with us?
I did saw a lot of literature incorporate emission penalty in the objective functions, and but this is challenged by a lot of referees, and it cannot accurately capture the emission it brings. And the emission is in the objective functions is mainly account for the emissions of the rebalancing trucks, but not the bicycles itself.
Okay. Yeah, so that's an interesting aspect. Okay, so do we have further questions or suggestions, comments from the floor? No further questions? Okay, so if no, I would like to thank Dr. Chui again. Okay, thank you. So, may I confirm that Ying, are you online? Ying is the first speaker here. Ying. Oh, Ying is not online, but okay. So then may I invite maybe the third speaker from HKUST. We have Dr. Kejun Du for his presentation, which is application for the railway system in Hong Kong. So the presentation title is a demand-driven ridership simulation model and unprecedented railway planning and operations preparedness. Thank you, Dr. Du. Okay. Yeah.
Okay, so today our presentation here today is about our academic industrial cooperation project with the Hong Kong MTR Corporation. We have this our MTR system simulation model platform and disruption behaviors estimation. Our topic is the on-demand-driven ridership simulation model, unprecedented railway planning for operations preparedness. So a brief introduction for our Hong Kong metro system, the MTR system. The Mass Transit Railway is the backbone of the Hong Kong's public transportation system. It covers over 90% of the peak hour travel demands every day. And it is a fairly large-scale network. It has 95 stations, excluding the airport express line. It has nearly 9,000 origin-destination pairs, and every day it has around like 5 million passenger trips. Most of them are concentrated in the peak hours, in the morning and afternoon. So, but however, for such a large-scale network, service disruptions are essentially inevitable, and they could cause significant economic and social impacts for the overall society. So how to mitigate the negative impacts from the unplanned metro system disruptions is our problem. And because the diverted or stranded passengers on the platform in the trains or in the whole society could cause pressure at interchange stations on road networks and could have safety implications. And therefore, the MTR Corporation needs to assign staffs and use different strategies to mitigate these impacts. So that's why we want to have a more precise evaluation of the impact from the metro system disruptions. So that is to say we want to estimate the passenger overflows and to evaluate the metro system performance. And then we break down the whole task into several sequential steps. The first step is to estimate the passenger route choice under normal conditions so that we could know that which passengers and how many passengers are actually affected by each or any disruption scenarios. And the second step is to predict passenger rerouting choices in a multimodal transportation networks, because the MTR network is not the only transportation network in Hong Kong. We need to consider road networks, the taxis, and any other modes of transportation, so that we could identify the rerouting choices of passengers from the smart card data and rationalize their behaviors based on the generalized route utilities will be introduced later. And the third step is to simulate the metro system microscopically with the predicted passengers' OD demands under disruptions. And so that we could simulate the passenger flows and other metrics to see the performance of the metro system under disruptions and test different kinds of strategies of deploying trains or staffs. So let's go to the first part of our framework, the passenger behavior estimation by simulation-based optimization with a computational graph structured metro simulation model. So let's briefly introduce the model first, the simulation model first. This is a flow-based dynamic metro simulation model, which is microscopic and based on and driven by critical events. So we assume that passengers income as in a Poisson distribution, and then we assume that passengers' route choices are simulated based on relative utilities of different routes, all the alternative routes between OD pairs. We could treat every route utility as an independent variable so that we could manually manipulate the route choices. We are essentially manipulating all the route choices between all the OD pairs as independent variables. So the whole system could have up to 18,000 independent variables simultaneously. And for the route flow proportions, we adopt the C-logic model for the route choice model. And then we use the event-based simulation based on which tracks the train arrival time, train travel times, train schedules, and passenger transfer times based on MTR data. And we simulate all these microscopic movements and actions of the passengers' interactions with the trains, the platforms, and the stations. Here we introduce the more microscopic structure of the simulation model. The passenger flow units, we call it PFU here, are simulated as continuous and dividable flow units, so that the whole simulation could be completely differentiable with respect to the with respect to the number of passengers. The PFU are conceptually identified as groups of passengers sharing the same OD pairs during similar times. We group them together as continuous number of passengers. And our model is an event-based simulation model. That means that because train movements are highly predictable in metro systems, so we take train arrivals at different stations as independent critical events. And then for each minute, we have a passenger arrival event for every whole minute, and we update the whole station passengers at every whole minute. And the whole simulation workflow is here at a top right flowchart. We see it reads all the critical events by chronological order and execute all the actions to the stations, to the platforms, to the passengers, and to the trains individually and iteratively to the end of the events. And because we focus on the key events, we reduce the computational power but still maintain the track of detailed passenger flows. And yes, we see at the top and the bottom right here, we see the station structure in the metro system simulation. We see that in each station we have different platforms for different lines towards different directions. And on each platform we have waiting queues of passengers where we simulate the first in and first out relationships of the passengers. So mathematically, we can have some analytical representations of the simulation outcomes of we have the passenger exit flows and link flows. We could write out the analytical representations of these outcomes throughout the simulation model, all the way from the incoming passengers down to the outcomes and the objective values for our calibration or optimization. We see the whole structure could be cast into this computational graph structure, and we see as long as all the errors here are at least almost everywhere differentiable with respect to the passenger flows, we could say that the whole structure is differentiable to the passenger flows. Therefore, we could use analytical or numerical gradients to do the iterative backpropagation and do the gradient-based optimization or calibration. And this framework does not limit objective variables for calibration or optimization as long as they are differentiable with respect to the flows. So we say that here we could choose different kinds of independent variables for calibration or optimization. In the green dashed area here, we see that we could we could use route utilities or route choice ratios as independent variables. That is to say, we have over 18,000 variables, like all the route choice ratios between the 9,000 OD pairs in Hong Kong in the MTR system. We take them all as independent variables and calibrate them all simultaneously in the green dashed area. And outside here in the orange or yellow dashed area, we see that we could also generalize the passenger route choices as with the route choice model, and we could calibrate or optimize for the passenger route choice model itself. So here, for better interpretation and better understanding for the MTR operators, we introduce how we estimate the passenger route choice model parameters. So we do this. This is a case study with real passenger flows from MTR system. On November 30th, 2022, we used real passenger OD demands. We used real exit flows and link flows. The simulation time was 1 hour. In the peak hour, we have 1 hour warm up so that passengers could be dispersed into the whole network. And we randomly sampled 15 sets of initial values to show the robustness of this model. And we see that they all converge quite well to similar values in the end, and the MAP of our objective value, which is the error of the passenger flows and link flows and exit flows, drops from over 45% to only 15%. But we see that we still have 15% of error because we see that the low flexibility of the passenger route choice model. Here we only have 4 parameters in the route choice model. It prevents the reconstruction of the actual passenger route choices, resulting in these higher MAPs. If we use all the route choice ratio as independent variables, we could bring the MAPE down to 7% to 5%. But we're not going to introduce it further here. But let's see the result passenger route choice model parameters here down at the bottom. These 4 parameters corresponds to the first one is the route in-vehicle travel times. The second is the transfer walking times, and third is the number of transfers, and the fourth is the commonality factor between different routes, which is a parameter for the C-logic model. So next. After we have the normal passenger route choice patterns or models, we could see how passenger reroute under disruptions. We analyze their behaviors using the smart car data. Let's take a look at the results first. We do the results first. So let's just briefly introduce our basic idea of identifying their behaviors. So we use regular commuters within the metro system as tracers or representative passengers. We identify their rerouting behaviors during a metro service disruption so that we could identify their behaviors, and we say that they represent the whole population in disruption rerouting behaviors. Who are the commuters? So because we do have the smart car data of the whole system, we could say that for one passenger, if on the same work day in the weeks before or after this disruption event, passengers have 3 to 4 or even 5 travel records of the same origin destination stations during the same period of time, we would say that they could be classified as regular commuters. And out of the over 30,000 travelers, we identified over 7,000 passengers, like 24.1% of passengers. We identified them as regular commuters with irregular behaviors. So we say that they are affected passengers responding to the disruption. So we categorize them into 4 different route rerouting choices. The first one is to reroute completely outside the MTR system or cancel the trip. We have around 70% of the passengers. And the second choice is to reroute partially outside the MTR system. That is to say, you use other modes of transportation to connect between the MTR system. We have 23% of passengers. And the last one is to stay inside the MTR system, but we have 2 sub-options. The first one is to wait until the disruption ends. We still have 5% of passengers who are going to wait and until the disruption ends, either on the platform or outside the system. And the last one is to reroute inside the MTR system. We only have 2% of passengers because in this case, not many passengers have alternative routes available inside the MTR system anymore. So how did we identify and categorize the regular commuters from the AFC data? So here we show some samples of the identification. So for the first choice, we have the rerouting completely outside MTR. We say that these passengers would have regular OD patterns on normal days, but they show no OD information or no related OD information on the disruption day. Then we say that they could be rerouting completely outside MTR or cancel the trip. So for the second one, rerouting partially outside MTR, these ones are more typical. Firstly, of course, they have regular OD patterns on normal days, but on the disruption day, they show related OD information on the disruption day. Either they have the same origin or same destination, or their ODs or paths going through the disruption section, like this example here from Kai Tak to Tai Po. So clearly they are using other modes of transportation to connect between Dawei and Taiwai and Shatian to connect, but they are still traveling from Kai Tak to Tai Po. And the third one is to wait until the disruption ends. Of course, they have regular OD patterns, normal days, and but they show the same OD pattern on the disruption day during the similar period. But they arrive after the disruption ends, and with significantly longer travel time, we would say that they are the passengers who wait until the disruption ends. And for the passengers reroute inside MTR with available routes, they also show regular OD patterns on normal days. They also show the same OD pattern on the disruption day, but we say that they take significantly different times than normal statistically, and also a critical and necessary condition for these passengers, this choice is that an alternative route is available for this OD. So to rationalize the whole thing, to understand, to have a better understanding and to quantitatively understand the passenger route choices under disruptions, we propose to use some kind of route choice model to capture the behaviors. So here we propose this hierarchical utility-based discrete choice model to categorize them into four lower level choices. And to do so, we have to integrate to use the routing information from the outside MTR road network. For this information, for this routing information, we used third-party navigation platforms such as Google Maps and Hong Kong e-mobilities and so on. We aggregated information and integrated them into the system and generalized them as route attributes, as alternative routes attributes for each individual route choice categories. And then we can generalize the whole route choices into generalized route utilities instead of more higher level, more lower level information, so that it could be generalized and used for any disruptions case in the future, no matter whether this kind of disruptions happened in the history, as long as we have sufficient historical data to train the model. And today, for our introduction, I'm going to focus on this red square here, this lower level choice of whether to reroute completely or partially outside MTR using other modes of transportation. So here we show our numerical results and some insights. To rationalize the decisions we have to analyze the route attributes. So here we focus on which route attributes are mostly correlated with the route choice with the proportion of rerouting completely or partially outside MTR. So we see that the original metro in-vehicle travel time and transfer working times are mostly correlated with the proportion of rerouting completely outside MTR. And we see a clearly negative relationship of the choice of completely outside MTR with respect to the in-vehicle travel time and the transfer working times of the original route without disruption. And so then we conduct some linear regressions of the choice proportions with respect to these attributes, and we see a clear negative relationship. And we say that our natural intuition is that like OD pairs that are more distant, meaning like longer trips would be harder for passengers to reroute completely outside MTR using other modes of transportation. Therefore, they are more loyal to the system, to the MTR system, so that they want to partially use the MTR system and only use other modes of transportation to connect between the disruption area or connect partially and use MTR for the rest of the trip, as long as MTR is working. So. And also because here these two graphs are only for like in-vehicle travel times, sensitivity, and because also the transfer working times are also correlated with the route choice ratios. We show this color plot here at the bottom. Here we see that as the transfer working time and the in-vehicle travel times increase, the number of passengers choosing to reroute completely outside MTR system is always decreasing. So we say that we could say that the sunk value or the sunk budget of the original MTR route act as a barrier for passengers to choose other modes of transportation, making passengers more loyal to the system. And we see some linear regression results here with different minimum thresholds of affected regular commuters. We introduced the thresholds as a minimum number of passengers between each OD, so that we could have a more representative results of the passenger route choice ratios. And we see that they are all clearly showing negative relationships of the route choice ratio with respect to the in-vehicle time and working time. And we conduct similar methods we use similar methods to all the route choices of all the passengers at different conditions. And then we integrated them into our metro simulation, MTR simulation platform under disruption scenarios for the MTR operators to use, which will be further introduced by May online here. So May, all yours.
Right. Hello, everybody. If no problem hearing me, right?
Good. Thank you. We can hear you.
Yeah. Okay. Great. Next slide, please. Yes, this is here we comes to the Metro simulation platform. And before I start, I really need to show my gratitude to Hong Kong UST for turning together this research subject into from project to product. So here we have the simulation platform. Please, next slide. That is. Next slide. Right. So currently I'm not in Hong Kong, but then even that I'm not in Hong Kong, I do realize that from the for the past few weeks, I think that we have some kind of service disruption that is not planned, that is very much spontaneous. That we have several typhoons happening in Hong Kong, and also we have money on track in consecutive days. So here is why we have to really plan at the outset how we're going to visualize the patronage impact under these situations. Next, please. So this is the what we call the user interface of interactive system that we have produced for the use by our frontline colleagues. And I've got to say that because of this forum, I've got to say that a lot has been done by both sides, and especially the UST team that have industrialized the solution, adopting the MTR standards in terms of project lifecycle, including configuration management and all sorts of standards we have to, comply within our in terms of project delivery. And a lot of workshops have been conducted with our users to really to understand how we're going to leverage the product to help them in their daily operations. Say, for example, in the case that we've given the example, we can leverage the model that was presented by Kerjin just now, and turn it into an interactive system by introducing and configuring the service delay and the level of suspension that we experience within our network. Say, for example, we can do the disruption configuration on the workstation by specifying the dates and what is the OD, that is the origin and destination demand data that we would like to do our ridership prediction to the base on. And digging deeper is that when we do the patronage prediction, we really need matching and the actual train service schedule, so that we can be able to give accurate results in terms of how we see the overall network is being impacted, especially at the pressure points, that is the interchange stations, where there could be a crowd gathering during the times of service disruption. And all kinds of parameters that we in the network, railway operations, would need to consider when we come across with a real situation of interruption. So next, please. So you can see that our system is actually connected to the live system that is in operation, that is a ticketing system. That we take the data to do the in and out base of the passenger count. And because we have leveraged the system to a lot of railway environment use cases, including the spontaneous incident, service disruption case that is maybe unplanned, like the monkey on track case. And also we have the new line extension that we would like to do the sensitivity test of how the new station would impact to the bring impact to the remaining part of the network, be it positive or negative patronage delta. And also, as you might be aware, that every year, in fact, we have got to plan for the train service of the next year, especially at some festive events, festive seasons, where we need to do overnight service or say for Chinese New Year. If you are really been in Hong Kong for the past years, that even Golden Week, we have very distinctive. We have a very distinctive patronage demand that are going across our network. Say, for example, for Chinese New Year, the first day, we probably have more patronage in Tsim Sha Tsui because of the parade that we have. For the second day, we have firework in Tsim Sha Tsui, Victoria Harbour. So the patronage in Wan Chai as well as Tsim Sha Tsui will be affected. And the third day, we have we have the Che Kung Temple in Taiwan. So a different period of time. So this is how we have leveraged the model's capability and to fulfill our daily operations need. And that is why we have taken the live data to do some prediction using the recent day of week patronage data into our estimation. And also we can be able to do customized patronage demand that is for perhaps new line extension prediction. And for the actual, we can actually leverage the same prediction model to look at how we have performed in the past. Say, for example, when there was a typhoon that is was hoisted and then it come off, and then immediately in the station, if during traffic hour or during daytime, then people will be rushing back to office. And in those 2 hours, how our entire network will be flooded, and whether we need to, dispatch more train service and do crowd control at respective or strategic areas. And the whole model can be able to facilitate us in doing so. Next, please. So going back to the monkey on track case, here we leverage the interactive route map to do the configuration of the case. So within the 1 hour of suspension, we can actually specify the number of train sets we have in the network, and we can be able to derive the length of the headway that we'll be supporting. And you can see that people are actually standing in the station watching the monkey. Why? Because as what Kelvin had mentioned, one of the our measured behavior is that if our passengers see what's happening, they would one of the options would be to stand there and wait for the service to resume, because they would see that the monkey, once it jump out of the track, service can immediately resume. So this is the kind of behaviors that we had measured, and we also expected these kind of behaviors. Next, please. So this is the simulation results. That is after the configuration, after we press on a button for the simulation to happen, we can actually project the next hour or even hours of patronage distribution across our network, minute by minute. So you can see the bar underneath that we can actually scroll and to observe what would be happening in the next 15 minutes, say, for example. As you can see that because the two stations, Chunwan Station and Taiwan House Station, had been suspended, there's no service in between these two areas. So what we can see from the simulation results is that at Chunwan Station, downline, down in our terminology, that means that going away from the depot. That is simply to say that from Taiwan House to Kwai Hing Station in that direction, and we can measure that. That is the on the platform, the crowdedness on the platform. That is a few times more as compared with to normal situation. So this is logical and something intuitive that we can understand why it happens. And at the same time, apart from our product is capable of knowing exactly how many people actually waiting for the train on the platform, as well as on the train. That is what we call the link flow. That is traveling on the train. And at the same time, this model is capable of giving us also the impact and the pressure at the interchange stations, especially. So that because usually when there is some kind of service disruption at a particular area, people would tend to do reroute or detour. So perhaps there are new areas and interchange stations that will be very much crowded with new rerouted passengers. So this is when operation side would have to step in and do some crowd control or passenger information broadcast. So these are the pain points and also the concern areas that we MTR as the operator will have to leverage the model to give us insights to. And so as you can see the different pop-up tables, you can see the top 10 or the top most concerned areas that we have to pay attention to. And the right-hand side bottom, the square, that's the table is showing us the transfer count, that is the interchange location that we would we will be expecting the differences. Say, for example, whether there are more or less people coming from the Chunwan line to change to Tongchong line at Lai King Station to get to the Hong Kong Island side, say, for example. All these will be able to be illustrated using this system model. Next, please. So as you see that our model has a lot of functions, also the report generation, that is how we leverage the data and the capability we've built in to observe what's happening within the network after the suspension. So we can be able to have the post-event analysis that is facilitated also by the system. Next, please. So this is a video clip that we can also show you, gives glimpse of idea one of the very important function that we have developed, that is the mega event economy. So far, we have our major Kaita Sports Park being introduced in the networks. So you can imagine that within the peak hour of our train service, if we have a sports park event that is with spectators having to disperse from the location, we are talking about 50,000 more passengers will be emerging in two of our stations in the vicinity of the stadium. So this is the impact we have to gauge, and that we have to be prepared And this model is able to give us to visualize what is the operational challenge that we have to tackle, and whether in what location we need to put more people in. Next, please. And using the platform's capability, we can be able to see that in those situations where the train surface is very much pressured and constrained, we actually can leverage the actual event end time to determine the level of service we need to put in. Say, for example, we observe that if the event's end time will be early, that is the light green one. We can be able to see that the peak of the peak capacity, the peak demand is not as high as the one green in color. So that means that, say, for example, people might, it is about the showtime ending at maybe early, that is around 6 p.m. So this is where people will tend to maybe go to dinner or shop around in the neighborhood of Kai Tak before they really get into the metro system network. So for the interest of time, I think I will stop here and wait for the audience to see if there are questions for us. Thank you.
Yes, thank you very much, MTR and also HKUST team. I do appreciate very much. This is a great project where the academics and also the industry so jointly work together to come up with something very helpful for the transportation industry. So I appreciate very much. So because of the time limits, maybe we can have one question. And I see there is one question online. For those offline, so we do have this platform. We can talk after this section, and then you can see the question, right? So it's in the chat box. Can you see the question? And also here, I think Dr. Du, you can. Yes, so it's a little bit long.
Maybe. So it's referring to the experience of the customer. In case of service disruption, usually if there is, we have several category of them. If it is kind of short, so passengers might tend to maybe wait for the service to resume, because usually it might not be a total suspension, but then it is a delay, service delay that is introduced, and we still have train service. It's just that the wait time could be longer. So it's the time that people might be frustrated, but then they still can catch on the train. But of course, it might be in the case of a crowded compartment for those cases. And for situations where, like the monkey case, that there could be service suspension. And this kind of information usually will be broadcasted centrally once it's identified, because the time to clear the track, there are sort of certain procedures that we have to follow. So this kind of situation probably we will be disseminating the information through our mobile app. That is the MTR mobile app there, where we will communicate with our passengers about the latest train service situation. And if it is really big enough, I believe that radio and also all sorts of media will be able to reach our public about the situation of the public transport, because this is also some kind of commitment we have with the government. And yes, and this model is, I would say, is to mainly assist our operators at the front line to visualize how and what our network will be impacted, so that we can be able to do some remedial action like whether and at which location that we should be dispatching extra help, like what we have now here is the extra shuttle bus and other crowd control measures that we will introduce to enhance and give a better customer experience to our customers. I'm not
Okay.
sure.
Yeah. Thank you, thank you, May. Yeah. So thank you very much. You have some more to supplement or no? Is it good? Okay. Okay. So thank you very much again for the to the MTR and also HKUS team. So again, so this is a great project. We learned a lot. So thank you very much.
Thank you.
Thank you. And then may I now invite Ying. So originally the first speaker, I think now she is online due to some unseen disruption. And then so now we would have the first speaker, okay, Ying, to share her research. I think she's online, right?
Oh yeah, but maybe can I wait for the next student to finish?
Sorry, I cannot hear well.
I'm sorry. Do we have for this
okay.
session?
Okay, then may I invite the last speaker to speak first? Okay, Ying. Okay, please. Okay. Okay, so now we have the the next speaker would be Dr. Zhu. Okay, so to share his research, where his title, the presentation title is Understanding Nighttime Pedestrian Risk in High-Density Cities, Causal Inference and Generative AI Approach. Yes.
Yeah, thank you, Professor Guo. Okay, so my name is Mu Yizhu. Now I'm a research assistant working for Professor Junshi Xu in the Department of Geography, Hong Kong U. So the topic I will present today is about daytime and the nighttime pedestrian crash risk. The title is Understanding the Nighttime Pedestrian Risk in High-Density Cities, Causal Inference and Generative AI Approach. Okay, so first is I will introduce some background about the pedestrian safety. So here I list a picture and compare the traffic crash deaths between Hong Kong and the world. So you can see there's a huge gap, huge difference for the pedestrian deaths in Hong Kong. Like pedestrian can account for over 16% of all traffic collision fatalities in Hong Kong, and it's much higher of that in the world. And it also highlights very high crash risk in Hong Kong in such high density, in such high compact urban environments. So previous research have also examined lots of factors related to the pedestrian safety, but there's still some research gaps, especially like in the nighttime dataset. So you can see some satellite imagery datasets are usually used to capture the urban surface information during the daytime, nighttime. However, its scarce or low spatial resolution limit its future application in the application at the street level. The street view imagery can provide a much detailed human angle or human perspective for the safety research. However, the nighttime street view imageries are often missed. So here we fine-tuned and applied a generative AI model to generate some nighttime street view imagery to capture this detailed information, and also build a causal inference model to detect the causal relationship between some building environment factors and the safety level of pedestrian. So next section is about the data. So the crash data set is from the Hong Kong Traffic Injury Collision Database, and we select the crash data from 2014 to 2019, and we also classify this crash data into daytime and nighttime based on the sunrise and the sunset times in Hong Kong and in different months. So in this, there are some basic statistic results. So you can see that in Hong Kong, the crashes during the daytime is much higher than at night, and it accounts for over 17% of all crash data. And next page is about the spatial distribution of the crash data sets. And yeah, we can see there's the crash data for daytime and nighttime. They normally focus on the urban central areas like the Kowloon Peninsula and Hong Kong Island, and also focus on in some rural areas like the new town areas like the Yong-Hong. And next, we want to understand the pedestrian crash, so that we built an index. It's called Pedestrian Crash Risk Index, PCRI, and this index can assign different weights to different severity levels of different crashes, like the slight, serious, and fatal pedestrian crashes, and so that we can fully understand the accuracy and the crash severity. So next is about the imagery data. So to ensure the temporal consistency between the crash data and the street view imagery data, so we download a total of over 110,000 historic Google Street View imagery using the Google API, and we also applied a semantic segmentation model to employ to conduct to extract some features from the images, like the roads, sidewalk, buildings, etc. And next, what we want to do is to convert the daytime images into the nighttime scenes, so that we manually collected some over 1,000 pairs of images of daytime, nighttime at different regions in Hong Kong, including some high-density areas and some rural areas, so that we can capture different kinds of urban settings. And then we input these images into a generative AI model, which is Decoupling, and train this model to convert the data scenes into the nighttime scenes. And this is the final performance of the images, nighttime images. And after the quality check, over 90% images are qualified. So we will use them to the subsequent analysis. And so now we have obtained many data sets. So next is to get some information from these nighttime images. So we quantify the visibility of the pedestrians and other elements at night, and therefore we build 4 pixel-based visual indicators, including the brightness, local contrast, inadequate lighting ratio, and glare ratio. Brightness can measure the lighting levels, and local contrast can measure how an objective differs from its surrounding areas. And inadequate lighting ratio and glare ratio measures dark areas and overexposed areas in the urban street environment. And we also calculate these 4 indicators in the whole images and in different urban elements, like the pedestrian areas, vehicle areas, sidewalk areas, and road areas, which is extracted from our segformer model. And we also incorporate some other sources of data like the road features and the building environment variables, which are treated as treatment variables and control variables in the following parts. So the third part is about the methodology. So in this research, the model we apply here is called double machine learning framework. So this framework can help us to estimate the unbiased causal effects of the treatment variables T on the outcome variables Y, and to remove the confounder effects of the covariates. So like this figure, we want to remove the impact of X on the T and the Y, and to estimate the direct causal effects of T on Y. So the workflow of double machine learning, DML, is quite simple. It includes two stages. Like the stage 1, we will build 2 machine learning models. One is use the X to predict T. One is use X to predict Y. And these 2 models can represent the causal inference, causal impact of the covariates, and we can compute the residues so that we can get the pure T and Y. And in the stage 2 is to estimate the causal effects. And yeah, you can choose lots of models like the linear regression or some latest model, causal forest. And the final part, so about the results. So first, here I present some spatial distribution of the crash data. Here we calculate the pedestrian crash rates, and you can see on the map, the spatial distribution is still uneven in Hong Kong. Like in some central districts, the pedestrian crash rates are still very high. And the next page is about the temporal variation. Like in the previous page, I mentioned the crashes during the daytime is much higher. But when we calculate the ratio, we can see it's quite different. We can see there's a peak of the share of fatal and serious pedestrian crashes during 4 a.m. and 6 a.m. So it's about the early morning, and the overall share of the fatal and serious crashes happened at night is quite a little bit higher than that in the daytime. And the next page is about the model output, and here the value of the model output is called average marginal effect (AME), and the value of AME means if we increase 1 unit of the treatment variables and how the outcome variable changes. Like for example, for the traffic sign density, you can see there's 2 values, one for daytime, one for nighttime, and for daytime the value is 1.22. Like it means if we increase 1 unit of the traffic sign density, the PCRI, which is our outcome variables, will increase 1.22, and the positive value is like a risk enhanced effect, and the negative value is a protective effect. So it's still about some traffic infrastructure, like the traffic sign and the traffic light. We can see the AME for these variables are positive in the daytime and nighttime. So this result it kind of challenges some previous assumption that the infrastructure can improve the road safety. This kind of like the quantity of the infrastructure can not directly improve the safety, and we will expand more in the next page. So next part is the AME of the nighttime variables, and yeah, for the brightness you can see the AMEs are positive, and for the local contrast, especially for the pedestrians and the vehicles, the ME is negative, which is protective, which can enhance the pedestrian safety level. And it's suggested that a clear detection or a clear boundary of the pedestrian or of the vehicles can help the drivers or help the pedestrian to detect the moving objects more clearly. And however, for the road and sidewalk, the local contrast is still positive. So it's kind of like on this surface on the road, the high local contrast is introduced by some like the vehicle headlighting, or introduced by some uneven lighting sources, which can bring more noise to this environment. And for the adequate lighting ratio and for the glare ratio, the AMEs are all positive. Like the dark areas or the overexposed areas are harmful for the pedestrian safety at night. We also calculate the nonlinear variation of different variables. Like for these figures, we can say the X is the original feature value, and the Y is the causal effects, so that we can see how the causal effects change as the feature values increase. So here I need some variables like for the traffic sign, traffic light, or the pole or the road or the wall segmentations, which is from the Google Street View imagery. And for these variables, the causal effects tend to decrease as their true feature value increase. Like this, it's like if we have more, for some locations, if we can detect larger areas of some traffic infrastructure, the environment tend to be safer. And back to our previous conclusion about the quantity, infrastructure quantity cannot directly increase the safety level. So that we get our conclusion is like the quantity is the number is not the key. The number of the infrastructure is not the key, because it can, in Hong Kong, such compact cities in Hong Kong, it can bring the visual overload, or it can bring some noise to the pedestrians or for the drivers. And in contrast, the ability to be detected is the key for this traffic infrastructure. And next, for some nighttime features, especially for the local contrast for the pedestrians, shows that the strongest protective effect is at value around 0.4 days. It is the most protective effect. And this means, this suggests that a moderate contrast can provide a strongest protective effect for pedestrian safety, and too high or too low contrast is not ideal. And for the inadequate lighting ratio or for the glare ratio, you can see these two variables are continuously higher when there are more visibility limited areas. So too dark or too light, too overexposed areas are harmful for the pedestrian safety level. So this is final part. So our research find that the built environment effects are highly time dependent and varies across locations. And the visual environment features also shape the safety outcomes. And for lighttime analysis, using the synthesized imagery provides new evidence on no lighting safety mechanisms. And also we find some actions that have been taken by the transport department, like they have removed some traffic signals, or improve the placement of this traffic infrastructure in some locations where the environment information is crowded, or to make the information more clean. Yeah. And yeah, that's all. Thank you.
Okay, so thank you very much. It's also another very interesting and also impactful project, research that we are focusing on. Okay, so we have some time for questions. Maybe one quick question from the floor. Yes. Okay.
Yeah, thanks for your. I think we have another. Just a quick one, because I'm focusing on safety where autonomous driving, and I also work on some collision data sets. And given your collected data set from the Google API, that is mainly focusing on the visibility, and then have you considered the different perception capabilities from different road users? Like different kind of drivers, like different ages, different their occupation, their minibus, their taxi driver, because they should have different perception limitations.
Yeah, thank you for your question. Well, because this research focuses on the pedestrian crashes, but yeah, we do not have such data set related to the information about the drivers or the driver behaviors, etc. So yeah, we do not consider such factors in this research, but we have some other real features related to the crashes, like the traffic volume, like the some traffic infrastructure, or the footway density, or the footbridge, etc. So that we can because we focus on the built environment. So yeah, the driver. Yes, yes.
Okay, so we have one more question online.
Removing street clusters from the idea of source so far and design guide of user behavior to this. Yes, thank you for your online questions. Like, because our research focuses on the nighttime pedestrian safety. So, and we use some imagery data, and we calculate several visual indicators from this data. And our final results is about it's mainly about the visibility of the infrastructure or of the environment. Like I mentioned here, for the government to improve the safety level of the pedestrian or other safety, what we should do is to increase the ability to be detected for the traffic infrastructure, and to reduce the overload information in some certain streets. So that we can help the drivers, help the pedestrian to detect the signal on the streets or detect each other easily, and also to simplify the traffic signals, or to harmonious the infrastructure is also a good way to help to improve the safety. Yeah, thank you.
Thank you, Mui. Okay, so let us thank the speaker again. Thank you. Thank you for the very interesting research. So may I now invite, so our next speaker, okay, Dr. Ying Sung, for her research. The title is a Modular Multi-Purpose Vehicle Routing Problem with Coupling and Decoupling for Collaborative Passenger and Freight Transport. You're using your laptop? Yeah. Oh, okay. I need to. Yeah. I think it's good. Okay, then you can switch to full screen.
Hello, everyone. I mixed up the time, so sorry for my late arrival. It's my pleasure to present this work here live at Hong Kong U. And this presentation will include the following 4 parts. Now let's begin with the introduction for this study. First, last mile operations are widely recognized as a costly bottleneck for the modern logistics. And studies estimate that 28% to 75% of the total supply chain costs can be accounted for these FLM operations. And these operations are typically characterized by spatially dispersed and fragmented demands, relatively short travel distances, tight time windows, and consequently low vehicle utility. So a core structural problem of these operations is the persistent separation of passenger and freight flows, which leads to increased efficiency when the e-commerce continues to expand. And to address this inefficiency, new technology named the modular autonomous vehicles have emerged as a promising remedy for this issue. So this MAV system consists of type-specific modules, including the passenger modules or the freight modules. They can couple as a platoon on the shared road path to enjoy energy savings, and later they can decouple to serve their own dedicated demands. So the key idea is to allow different types of modules to move jointly while reducing the energy consumption and preserving the service quality specific to each demand type. The existing combined transport passenger freight systems for this first last mile operations can be broadly grouped into 3 categories. So the first category is a shared cabin system. While it is operationally simple to implement, it may compromise the service quality and increase passenger travel times. And the second category relies on the shared infrastructure system, while maintaining the physical separation. However, these systems typically fail to provide the on-demand services. And the third category uses the latent capacity from crowd shippers, such as recruiting the ordinary commuters or the occasional drivers. However, order matching is difficult, and it is likely to increase the detour distances for these commuters. So we have 3 insights for a better transport system. First, we need to preserve the type-specific service quality and provide on-demand pickup and drop-off services while achieving the energy savings through joint movements of different demand types. So we propose an MAV system for this combined transport. We consider a multi-depot setting with separate freight depots and passenger depots. Each depot operates a fleet of type-specific MAVs. And freight requests and passenger requests are distributed over a realistic urban road network, which also contains the ordinary intersection nodes. The key operational features for this system include first, type-specific modules can couple and decouple en route at any network node. And the platooning savings are captured explicitly in this system. To reflect the realistic urban road operation, we permit node revisiting and also capture the path deviations between consecutive visits instead of simply following the shortest path. And we also differentiate the service quality with dual waiting time limits, a per visit waiting limit and a whole trip waiting limit that are type specific. Looking at the existing MAV studies on the combined system, we can observe several limitations. The first is that most studies simply use simplified network representation, while our work consider modeling on a directed road graph with node revisiting. And secondly, most restrict their coupling and decoupling operations at depots or customer nodes only, and assume fixed platoon once they depart from the depot. While our work considered coupling and decoupling at any network node and handles the dynamic en route platooning. And as for the waiting time restrictions, most consider the soft penalty inobjective or even have no restrictions on intermediate waiting, while our work consider both the soft penalty as well as the hard waiting limits that are type-specific. And finally, when it comes to the routing decisions, different from the previous studies, we simultaneously address the customer visit sequences as well as the deliberate path deviations between visits. So the main contributions are fourfold. First, we introduce a new problem, which is a multi-depot modular vehicle routing problem that integrates the type-specific MAVs with dynamic platooning. And secondly, we establish a new model, which is a mixed integer programming model based on a time-space network. We also formulated 4 additional benchmarks. And to deal with the real-world large-scale instances, we propose a 2-phase heuristic algorithm. And finally, we conducted extensive experiments on 5 real-world road networks of different scales, demonstrating the effectiveness of the model and the algorithm. Now let's turn to the mathematical formulation. We will jointly optimize the following 5 levels of decisions, which are the customer assignments, visit sequences, path choices between visits, departure and waiting schedules, as well as the dynamic platoon membership en route. And the objective is to minimize the weighted sum of total energy-related distance while accounting for the platooning savings, total passenger trip durations, and the unserved requests. We discretize the timestamps over a planning horizon and construct a time-space network. 3 types of time-space arcs are defined, which are the moving arc, waiting arc, and serving arc. And on this time-space network, we define several families of decision variables. Respectively, they describe the itineraries of each MAV, the customer assignment, and to record service amount, track vehicle load, assign the platoon leader and follower on each time-space arc. We also have groups of constraints. First, we have constraints on the MAV travel behavior and the customer assignment constraints. We also have constraints on the waiting behavior, enforcing the per visit waiting limit and the whole trip waiting limit for each vehicle type. And then we have constraints on MAV's platooning behavior, ensuring that a module can only join 1 platoon at each time-space link, and platoon size limits are also observed. Finally, we have constraints on the vehicle load as well as the variable domains. And we also formulated 4 benchmark models. The first is a no detour model, where MAVs can only travel on the shortest path between consecutive visits. And second is a no collaboration model, where platoons can only be formed by the MAVs of the same type. And the fixed platoon model, where platoons can only be formed at the depots and remain fixed once departure. And finally, the no platoon model, where no platoons can be formed. So every modular vehicles just operate like a regular taxi. And because this MILP model is intractable, so we introduce a 2-phase heuristic. We first represent the solution using a compact form, focusing on only the service sequences for each MAVs. And then we introduce an extended form to explicitly insert all the intermediate nodes that a vehicle actually traverses. And this algorithm proceeds in two phases. In the first phase, we use an elite list ALNS, the adaptive large neighborhood search, to optimize the customer assignment and visit sequences. And we also maintain a set of high quality, but not necessarily optimal routing sequences. And in the second phase, for each sequence in the elite list, we employ a path optimization heuristic embedded with a scheduling model. This scheduling model optimizes the platoons and schedules on the extended form of routes. And now I will introduce the experiments. We have evaluated the performance of our heuristic based on 5 road networks. And the number of nodes ranges from 11 to nearly 400. The number of directed arcs ranges from 28 to almost 800. And the planning horizon scales from 1 hour, which is 60 minutes, to 4 hours. And at each network, we generate 12 random instances with different numbers and distributions of requests. On small instances, we compare our heuristic with Group B, and we set a time limit for Group B for 3 hours. And from the last 2 columns, we can see that our heuristic obtained the optimal solution for all 12 instances with 0% objective gap, while requiring only less than 0.3 second CPU time, which is much faster and efficient compared to Group B. And on larger Anaheim network instances with only delivery requests, we compare our method with a published algorithm, which is a 3-stage algorithm, with only minor adaptations. And we can see that across the 12 instances, our heuristic, the improvement of our heuristic compared to the 3-stage algorithm is nearly 19.3%, showing great efficiency of our method compared to the existing one. And we also compare between the 5 models with different levels of saving ratios. And from the left plot shows how the total objective value changes with different saving ratios. And we can see that all the models show a decreasing trend, indicating that when the saving ratio increases, the total objective decreases. And the main model, the MM, shows consistently lowest objective value across all the saving ratio levels. And the right plot shows the objective gap versus the main model. We can see that when the saving ratio increases, the gap also increases, which demonstrates that our main model have more advantage when the platooning can produce greater savings. And now we do a further sensitivity analysis on the dual weighting limits. Here are some key conclusions. First, when the freight MAVs cannot wait, the passenger weighting flexibility has no effect at all. And second, the decreasing trend of both lines when the freight waiting time relaxed shows that the freight waiting flexibility is the dominant factor for the energy reductions. And third, the passenger weighting affects the solution only when the freight weighting is already loose. And then it only produces a modest increase in the total passenger trip durations. So to conclude, in this presentation, we formulated a multi-depot modular vehicle routing problem that integrates dynamic platooning on a realistic directed road network. We established a mixed integer programming model based on the time-space network, and we proposed a two-phase heuristic algorithm for this problem. And finally, we conducted experiments to show the effectiveness of the proposed model and the algorithm. So thank you for your listening and welcome any questions.
Yeah, thank you, Dr. Sun. Yeah, also a very interesting piece of research. Okay, we have some time for questions. Do we have questions from the floor or online? So maybe I can start with a question. So actually, to my understanding, so you want to switch it back to full screen. Okay. So, okay. So then my question is like these types of vehicle routing problems, I think like they have been studied for decades, right? So there are many different variants, and then so what you're considering is something I think is even more complicated, and then so but of course so it's more timely. So my question is typically we need some ways to solve it, like exact methods. Typically they encounter some computational burdens, right? So that's why you move it to heuristic. Then my question is, when you design the heuristic, so there are different types, right? You have adaptive large neighborhood search, you have like even you have maybe taboo search or simulated annealing, or like you have genetic algorithms. So like from the literature or from your experience, what is your advice, like what types of algorithms you have some ideas, like which types we have to choose, or like for this particular application, like what would be the key tricks when you deploy your heuristics?
So first, I think the performance of each algorithm heavily relies on the design of the operators.
Yeah.
So, I mean, when you design the operators, you need to think about what is the key decisions you'd like to optimize at this phase. And then you choose the algorithm that can better fit the operators that that can be adapted to this problem. And then I think, from my experience, I actually tried a lot of different algorithms and found which is better, just from the solution qualities.
Okay, so my next question, actually, this is what I was thinking, like in your problem, what would be the key tricks when you design these operators for this particular application as compared to traditional vehicle routing problems?
A key trick is that I need to consider how to coordinate the time for platooning instead of just optimizing the routing. So initially, actually, I combined the routing and platooning decisions within a one-phase ALNS framework, but actually I found it cannot work. That's why I decompose it to a different phase. So, I mean, I decompose the decisions into two levels so that I can design operators for routing and platooning respectively.
I see. Okay, so just one final question I have in my mind is, of course, so you have this operator, so you can kind of change the structure of the solution, and then so you tried. So my understanding is you change the structure of the solution, and then so you search for some better ones, right? So basically, you have a search method. Then and other important aspect is about the initial solution, right? So how do you see, like also from your experience, so how important the initial solution is, or like the search strategy is more important?
Yes, the initial solution is very important because if you start from a very bad solution, then the searching process will become very difficult. So, and in this algorithm, I designed the initial solution based on a previously recognized method.
I see.
Yeah, and only focusing on, yeah, so the initial solution is not my focus.
Yeah.
I only care about to generate a high quality initial solution for only for only optimizing the route.
I see. So your way is like you could have like some solutions from existing methods, and then you start from there, and then so you try to improve.
Yes.
Okay, I got it. Okay, thank you. I think I finished my questions. So do you have further questions from the floor or like online? If no, so I would like to thank all the speakers again. So for the, I would say, so for all the very interesting and also for practical applications. And for those who will be joining the next section, so we will start in 5 minutes here at Hong Kong U and also online, so in the Zoom room. Okay, thank you again for your participation. Thank you.